Okay, so let's start with the lecture. So today I will teach you about the third adsorption isotherm. Uh, This is called the BET. So this is the third adsorption isotherm. It is called the Brunauer Emmett Taylor isotherm, and simply we call it a BET isotherm. And BET is coming from the first name of all these three scientists. Actually, these are the three scientists who developed this isotherm, and we call it a BET adsorption isotherm. And this explains the physical adsorption, particularly the multi-layer adsorption. So we have discussed before in the Langmuir adsorption isotherm about the monolayer adsorption, and this is the multi-layer adsorption. So BED is talking about the multi-layer adsorption of gas molecules on a solid surface and serves as the basis for an important analysis techniques for the measurement of the specific surface area of the materials. This is very, very important. Currently, if any one of you have learned or know about the nanotechnology or the nanomaterials, actually this is the adsorption isotherm we use to measure the specific surface area. If you know the specific surface area, that means it is going to depend on the particle size, and nano is dealing with the size around 1 to 100 nanometers, and it is actually the increase in the surface area as compared to the commercial materials available. And this is one of the way to confirm the nanomaterials or to check their surface area, how it is going to depend on the particle size. And this adsorption isotherm is very, very important. Actually, this is the a big instrument which involve the measurement of the surface area or the specific surface area. So these are in 1938, actually, these are the scientists, Stephen Brunauer, Paul Hu Emmett, and Edward Taylor. So their last names are coming with the theory, which is called the BET adsorption isotherm theory. So further, the difference between the earlier what we have studied, the Langmuir adsorption isotherm and the BET isotherm. This is the case for the Langmuir adsorption isotherm, which is called the monolayer adsorption. This is the surface of the adsorbent, and this is the adsorbate which is going to adsorb on this surface. And if you have a look, this is the monolayer adsorption, and here this is also the adsorbent, but this is the first layer monolayer, and then it is the second layer and third layer and so on. So that's why this is called the multi-layer adsorption, and this we will study in the BET adsorption system. So this is the only difference between the Langmuir adsorption isotherm and the BET isotherm. So let's first have a look in a similar way what we have learned with the other Freundlich adsorption isotherm and the Langmuir adsorption isotherm. So of course, BT isotherm is going to be depend on certain assumption. So first we are going to discuss all these, and then we will move to the theory and its equation. So with the BT isotherm, adsorption surface has a definite number of the active centers which are energetically equivalent and are capable of retaining adsorptive molecules. This is the same assumption we have already discussed in the Langmuir adsorption isotherm, because this is going to be depend on the physical adsorption, and each active center should be equally important and having the same energy to adsorb the molecule of the adsorbate. Second, for simplicity's sake, the interaction of the neighboring adsorbed molecules in the first and subsequent layer, that is in the same layer, is neglected because we have studied the multi-layer adsorption. So we are talking about here, this is the first layer, this is the second layer, and this is the third layer. So interaction between the adsorbate and the adsorbent is important, but here we are going to assume that the interaction of the neighboring adsorbed molecules in the first layer or the subsequent layer in the second or the third layer. Neighboring molecules mean if this is the molecule, it is adsorbed on this surface, so its interaction with the neighboring molecules is neglected. So importance over here is we are only going to consider the adsorption between the adsorbate and the adsorbent. This is all about the second assumption. So the third assumption is each molecule of the first layer is the possible center for adsorption and formation of the second layer. And of course, each molecule of the second layer will be the possible center for adsorption of the third layer, and this will be going on so on. So because the second layer will only be absorbed if first layer is providing the active center for the absorption for the second layer. And third layer will only be absorbed if this second layer will provide a sufficient active center for the absorption for the third layer. So if it is not going to happen, then there is no possibility for the multi-layer absorption. So this assumption is also very important when there is the formation for the multi-layer absorption. The fourth one is also relevant to this one. It is assumed that all molecules in the second and subsequent layers have the same partition function as in the liquid state, which differ from the partition function of the first layer. So partition function mean this is the same as you may consider the uh, equilibrium constant, because here it is the partition of, let's suppose, the this first layer, adsorption of the first layer with the adsorbent and with the second layer. So how much of molecule of the first layer are adsorbed, and then they are partitioned with the second layer. And similarly, what would be the partition function of the second layer? The partition of, let's put this molecule with the third layer and with the second layer. So this is the partition function for the second layer. So what we are going to discuss over here, that second and each layer have the molecules are having the same partition function, but it should be different from the first layer. And why it should be different? Because in the first layer, it is written over here, because this process is a very important, adsorption, and at a certain condition it is going to be desorb, adsorb, desorb, and there should be a equilibrium between these two processes over here. So for the how the first layer is different from the second layer, because in the first layer the adsorbate may be a gas or the liquid, and adsorbent would be a solid. So this, the gas is going to adsorb on the solid, or the liquid is going to adsorb on the solid, as indicated over here. This is the solid, and this first layer is the adsorption on the solid surface, but it is different from the second layer. How it is going to be different? Because the second layer may be the gas or maybe the liquid, depending on the nature of the adsorbate. If it is a second layer, if the adsorbate is the gas, then of course second layer will be the gas, third layer will also be gas, fourth layer, fifth layer, all the layers will be the gases, as the adsorbate is the gas. And in case of the liquid, second layer will be the liquid, third layer will also be liquid, fourth layer will also be a liquid. So that's why this partition function of the first layer is different from the partition function of the second and the third layer. And second, third, and fourth layer will be having the same of partition function, because there is no difference between the second, third, and the fourth layer, but there is only difference between the first layer as compared to the second or the third layer. And this I have explained. This difference is due to the adsorption of adsorbate with the solid, and this is the second layer will be the gas, let's suppose, and the adsorbent here it is the solid. That's why this partition function of the first layer is going to be different from the partition function of the second and the third layer. So all these are the assumptions for the BET, and this is again a little bit more explanation how the multi-layer adsorption complex is formed. And this is the first layer. First layer is the active center. That means this is the adsorbent and this is the adsorbate. Maybe the vapor, mean it is the gaseous form, or maybe the liquid. So here it is the active center when it is the first adsorption uh, complex is formed. That means adsorption of the adsorbate on the adsorbent. Then there is the formation of the first layer, and here you can say this is the single complex is formed. And then this is the first layer which is adsorbed on the surface of the adsorbent, and this is going now to provide the active center for another layer of the adsorption of the vapor, and then the double complex is formed. That means second layer of the adsorption will form. So when this is going to be acting as the active center again for the absorption of another layer of the vapors, and then the third layer is formed, and this process will going on as it depends on how much is the activity or the active center to retain the further molecules of the adsorbate. So this is the way how can you explain the formation of the multi-layer adsorption complex. So here, actually, we are not going to derive the equation. All these four equations which are given over here are the same. There is no difference between all these four equations. So I have actually gathered all these information from the different books, and I'm going to explain you all these equations are the same. Let us start with the first one. I will talk about what about all these parameter in the next slide. But here, just to compare all these four different equations, and this all these are called the BET equations. So maybe we will be using this to further explore the properties or to calculate the surface area, because surface area is very important as I have explained before. So let's suppose this is the final equation, and if this is the same equation, and if you want to move to this equation, actually this is 1 over P naught, and when you take the LCM of this one, so 1 divided by 1, that means P multiplied by 1 P naught minus P divided by P naught is going to cancel out, and 1 P is left. So P naught minus P, and here you have a look, this is the P naught minus P, and it is, when you take the LCM, this would be the dividing the whole equation, and this P naught is going to cancel out, and this will remain the same. So this is just the different manipulation of the results by using these different equations, but there is no difference between equation 1 and 2, and this is remain the same as in the four equations. There is no difference over here with this factor and with this factor, but only there is a difference between the first one factor over here, that is called the y-axis. Let's suppose how it is like this form. Here just P over P naught is taken at Z, and where is P over P naught, it is mentioned with the Z. So this will be the Z, 1 minus this will be the Z, P over P naught will be the Z again. There is no difference between this and this equation. Now come to the final another equations over here. This is the same again. As I have taken LCM over here, you can take also LCM over here. So LCM will be the P. When you take the LCM of this one, P, and P is going to divide with the P1, and then it will remain P naught multiplied by 1, P naught. And here when you multiply 1 by P, so it will be converted into the P naught. So net result will be the P naught minus P divided by P. So it is the double division. So you may convert into the upper form. So this equation will be converted into again this equation. So these are just taking the LCM and converted into the this simple equations. So you can do homework at home, but I have already explained you how all these equations are converted to this main equation. There is no difference between all these four equations. So because you will be seeing in the notes somewhere equation this is given, somewhere this is given. So I have taken all these possible equations from the different books, so have compared all these between each other, and there is actually the net result is there is no difference between all these four equations. So now exploring further with the equation. So what is the actually the important over this C is the constant. In a similar way, what we have discussed in the Langmuir adsorption isotherm, where we use the K, and here we are using the C, and this is actually called the BET constant. There we use the Langmuir adsorption constant, and but all these are the equilibrium constant. So you can say here this is a BET constant, or you can say this is simple to the equilibrium constant, or we will actually calculate the value of this later on. So how it is equal to the thermodynamics parameter. This is the exponent delta desorption and delta of the evaporation. Or simply you can say this is the change in enthalpy for the desorption and change in enthalpy of the vaporization. So this is just the difference between these two enthalpy divided by RT. And in chemical kinetics, you have learned the Arrhenius equation. So this is similar to the Arrhenius equation, where we use K is equal to exponent E del activation energy minus activation energy over RT. So this is by resemblance, this is similar to the Arrhenius equation. So you may go back and look what is the Arrhenius equation over there. So this constant, that means it is explained over here. It is a constant which is large. It may be a large or maybe the small. So when it is large, that means this factor would be greater than this. So let's suppose this is 2 minus 1, then the value would be in positive. So that means how much the factor of change in enthalpy of the desorption, or you can say the enthalpy of desorption would be more, then there should be a more value of this adsorption constant. So what would be the difference between these two at desorption and the vaporization? So actually this is the multi-layer adsorption. It is going to depend on the pressure of the gas and the nature of the adsorbent, of course. So how can you differentiate between the adsorption and the vaporization? Actually, this first layer, as I have explained before, this is adsorbed on the surface of the adsorbent, and we use the term desorption only for this first layer because this is adsorbed on the adsorbent. And if you consider the second layer is adsorbed on the first layer. So all the first layer molecules or the second layer molecules or the third layer molecules are the same. Let's suppose these are the gaseous molecules. So they will be a gases, or they, if they are liquid, they will be a liquid. So for the second, third, and the subsequent layer, you must use the word of the enthalpy of the vaporization, because these molecules are going to evaporate out of the first, and of course the first layer is going to evaporate, then it is going to the second layer, but it is more appropriate to use the word desorption for the first layer. So this is all about the enthalpy of the desorption and the enthalpy of the vaporization. Desorption from the first layer and vaporization from the second and third and the all the subsequent layer. And when the desorption, change in desorption is more as compared to the vaporization, then this constant will be having a more value, or you can say this is large as compared to the vice versa. So this is all about the constant or the equilibrium constant, or we can more better to say this is the BET constant. So what is the V? V, P, Vm and P naught is left. So V is simply the volume of the gas, that means adsorbate, which is adsorbed at pressure P and temperature 1 at specific pressure and temperature. Temperature should be the constant. That's why this is called the isotherm at constant temperature. And Vm is the volume of the gas, of course, again adsorbate, but adsorb to form a saturated monolayer. So there is a difference between V and the Vm. V is any volume of the gas, but here Vm is this the volume of the gas to form a monolayer saturated monolayer. So what does it mean? That means when all the active center on the adsorbent are occupied, so the layer becomes saturated. At this point, the volume of the gas is called the Vm. So this is the difference between V and the Vm. And similarly, P naught would be, P is the pressure of the gas, and at any at a specific temperature, and of course the volume. And what is the P naught? P naught is the similar to the Vm. It is the saturated pressure of the gas at temperature T. So these are actually the Vm or P naught are the volume and the pressure at the saturated state. So again, P over P naught is left. Actually, there is no need to separately define this one, because we have already discussed before. But it is actually called the relative vapor pressure of the gas, because P is going to change, but P naught is not going to change, because this is the saturated vapor pressure and this is having the constant value. And because this is the relation between the two pressure, that's why this is called the relative vapor pressure of the gas. So this is going to be actually we are winding this one with the explanation what we are getting out of this one uh, equation. This is the same BET adsorption isotherm, and this is the y-axis. This is called the C because this is the constant. And why it is C? Because this is the BET constant, this is the saturated volume, and as I have explained before, all these constant will remain the same. That's why this whole factor 1 over VMC is called the constant, and that is called the intercept, because this is the y equal to mx form. And this is again a constant, c minus 1 or vm c, all these are the constant. That's why this is called the m. And p over p naught, it is called the x-axis. So this is the x. Of course here p naught is the constant, but it is up to you. If it is you are taken with the slope, you can also do, but it is more appropriate to use p over p naught. You take the whole as a relative vapor pressure as a x-axis. So that means this is the slope, this is the intercept, this is the x-axis, this is the y-axis. So why you have taken this constants, all these constant as a slope, because this is going to multiply with the x-axis. That's why this is called the slope, and this is the independent constant. That's why this is called the intercept. So these are written over here. Intercept will be 1 over VMC and slope will be C minus 1 VMC, and all unit will be equal to CM minus cube, or it may be per centimeter cube, or sorry, or the per decimeter cube or per meter cube. It depends on the what would be the unit in volume you are using. Actually, this is the inverse of the volume, because 1 or c are the constant, and when you take the volume in centimeter cube, and 1 over v will be the per centimeter cube, and similar way all these are the constant, and 1 over vm the unit would be cm per centimeter cube. So here you are going to plot the graph on the y-axis, this whole factor on the y-axis, this on the x-axis, and when you plot a graph, it would be having a positive slope because the slope over here is plus. Then it is having the intercept on the y-axis, and what would be the intercept from 0 to here? This is the intercept. From intercept you can calculate the Vm, and when you put the value of Vm over here, you can get the value of the C. So actually this is the slope, and the slope whole is this, and this is the intercept. So I am going to further to simplify this Vm, how you can calculate the Vm, because this is the most important parameter over here. This parameter Vm we will be using to calculate the specific surface area in the next class. So this you can easily calculate. Actually, when you take the reverse of slope plus intercept, this will be equal to the saturated volume. And here the reason is given over here. Actually, this is the all about the explanation why 1 over slope plus intercept will be equal to the Vm. And this is the, because when you add the slope and intercept, slope is this and the intercept is this. Sorry, I think it is the reverse. Intercept is 1 over. So this is the intercept and this is the slope. So when you add all these two, this is converted into the Vm. How? Because in the denominator, these are the same. So you can also take the LCM as a VMC, and VMC is going to cancel out. One is left. And when you multiply the there, actually this is just I have taken the reverse of this one. So when you multiply VMC divided by VMC, it is 1. 1 multiplied by 1, it will remain 1. So VMC divided by VMC 1, 1 multiplied C minus 1, it will be the C minus 1. So actually I have just skipped the replacement of this factor over here and this factor over here. So you can easily do, there is no issue at all. So this minus 1 plus 1, this is cancel out. What is left? C over VMC is left. And then again, C is cancel out. 1 over VM is left. So this is just the rearrangement. If you take this the left hand side, and this will become 1 over slope plus intercept. So you will be directly calculating the slope and the intercept from the graph, and just to take it the inverse of the slope plus intercept, this will directly give you the value of the Vm. So we are not going to actually first to put the value of C over here, then put the value of the VM over here, then to calculate the C, or you can take the reverse of this. This is a slope. First, you have to put the value of C and then to get the value of Em. So this is going to be more complicated. So this is the simple calculation for the Vm. So we will be just taking the sum of the slope and the intercept and dividing by 1. This will convert to the Vm. So this is all about our today lecture.